Okay, so this is my Calculus 2 presentation, end of the year project. It's about parametric equations and Taylor polynomials, and it's about how they relate to computers like calculators and then simple animation. So I'm going to start with a quick little explanation just so that we can get familiar with what they are. So the Taylor polynomial is basically a way to simplify complex equations that would be really hard to try to take derivatives of or just to find out things about. Also, if the equation is centered around zero, is called Maclaurin. That's kind of not important. Anyways, this is the process. First, you just plug in if it's centered at zero. First, you plug in 0, good. Then you do the derivative of 0 divided by 1 factorial, which is just 1, so you don't really worry about that. And then you add in the first x. Second derivative divided by 2 factorial, that's the x squared term. Third derivative, plug in x. Third factorial, that's the cubed term. And you go all the way until however many degrees you want to do. But as I already said, this allows us to estimate more complicated functions. Another thing is the higher the degree you go, the more accurate this fake equation will be. Basically, I'll talk about this later, but these are only using plus, this might be minus, so plus or minus, and it's using times and divide, which is really easy for a calculator to calculate, versus things like sines and exponents and all this stuff. If you try to find certain terms, it's just really confusing for a calculator sometimes. Next, I'll talk about parametric equations. And I didn't really know what the rule exactly was, but here's how I think of it. Normally we know x and y just in a graph. This adds, parametric equations add in t to let us know a third thing about the graph. So this is our example. X is equal to 5t plus 1. Solve for x. Here's the work. You can probably do it yourself. And anyways, you get x minus 1 over 5 is equal to t. So this is what t is equal to in this equation. Plug it into the y equation for how y is related to t. La-di-da. And then you get y equals 2x minus 7/5. So this is basically a system of equation, but because it's related to t, it allows us to know a third variable. So it shows the behavior of x and y in relation to t. And this little note down here, as there's another thing we like to know about these, is what is the behavior of the graph as t increases or decreases. In this one, as t increases, so does the graph. Okay, that's the end of the little introduction. So I'm going to start out with talking about Taylor series. And I have one about a real-world example about how they'd be used in animation, but I just wanted to do one example about why they're even used in general, because when I first heard this, I thought to myself, well, I can push into my calculator e to the x, or I can put in my calculator e to the 2, and it just spits out the answer. I don't actually know what it is, 4 point something. So I thought, why would I need to go through this whole entire process for a Taylor series? It seems like a big waste of time if I can just put into my calculator and it'll spit out the answer. And then when I was researching this, found out that calculators actually use Taylor series. This is going to be using Euler's number for this, but it really applies to anything like pi would work because it's rational. Sine would work, sort of similar, or any trig, I should say. But basically because it's wavelengths and periods, and that's what our next example is going to be about, so I'm not going to talk about it too much. But in this one, I just want to go through a quick example of how, and I have it on Desmos too, how you would go about making a Taylor series for this. So first, f of 0 is just going to be e to the 0, which is going to be 1. This is our constant. And this is a pretty easy one, because the derivative of e to the x is just e to the x. And we plug in 0, which is going to mean that it ends up being 1. Remember, the first time you do this, you have to divide it by the factorial of 1, which no one really does because that's just 1. I'm not going to do the derivative again because it's the same thing. This time divided by 2 factorial, we get 1/2. This time divided by 3 factorial, so we get 1/6. This time divided by 4 factorial, so we get 1/24. So now, this is 4 terms, so our final equation would be constant plus 1x, because these are the coefficients, plus 1/2 x, so x over 2. Oops, and this is supposed to be squared, because it goes up. Plus x third over 6, plus x to the 4th over 24th, so on. And basically, what this allows a calculator to do is, instead of thinking, oh, well, what's e equals to, I honestly don't know, but it goes on forever, and then you have to square it, so you have to times it by itself, times 2, and keep in mind the calculator can only store so many digits of Euler's number. What instead this allows us to do is, say we're looking for e to the 5th. If a calculator had to go through this 5 times, a super long, never-ending number 5 times, repeating over itself, it would just be really slow. But because we have it in this simple equation form, 1 plus 5 plus 25/5 plus, I'm not going to go through it all, but doing it like this makes it way easier. Why? Because it's just pluses. Sometimes these will be minuses. You got multiply sometimes and divide. It's just basic arithmetic. So, and if we went on to 10 terms, it'd be even more accurate. So I'm going to go to my next example. Oh. Yeah, I have a graph for this. No, I don't. I'm going to go to my next example now. So for this next example, we're actually going to talk about something an animator would use. Say you had a ball and you're trying to animate it bouncing along, you know. So maybe one way you could do this is with sine of x. You know, oscillating, it'd be good. But there is a problem, which is that when you're trying to animate something like this, we run into the problem again. Basically, trig functions are really challenging for computers. You have intervals, never-ending numbers sometimes, and it's just hard to calculate, just like we showed with the previous option. So, if we wanted to animate this ball, and say we only had to do it for 2 seconds, if you only had to animate this ball for 2 seconds, why would you put in a never-ending function that's going to take a computer forever to try to animate? So we can just use a Taylor series because it's way easier, it's going to make it way smoother, and it's just, there's not going to be lag. So I'm going to sort of go through this, maybe not all of it, but you get f prime of 0 and sine of 0 is 0, f double prime of 0. So we go to, what's the derivative of sine? Cosine x. Plug in 0, you're going to get 1 divided by 1 factorial, 1. So this is the first coefficient. Cosine's going to go to negative sine, just like we saw the first time. This is going to go to 0. We can skip it. That's to the 4th. These stack up fast. Negative cosine of x, which is going to be negative 1, now divided by 1, 2, 3. Negative 1, 6. Anyways, I did this for a while on another piece of paper, and the equation I eventually got was, here's the first term, and remember, is going to go back between sine and cosine, so the sines are going to cancel out. So this is the final equation. X minus x to the third over 6, that's this one, plus x to the fifth over 120, minus x to the seventh over 5040, plus x to the ninth over 30, what is that? 362,880, so very big number, and this could go on for a long time. But I'm going to show you on Desmos why this is definitely good enough for what we would need, because it'll make it way easier. Okay, I'm pretty sure it's going. So I was just talking about the ball example, and I'll just go through the graph. So here's the sine graph. The trig graph goes on forever. And here's this one. And if you look, they're pretty much the exact same for this little area. So here's what I did. I just wanted to show the ball bouncing along, and I had ChatGPT help me figure out this coding stuff because it was kind of confusing. But as you can see, it splits right here. But for this small amount of time, which is maybe all we would need, it's the exact same. And look, it does split a difference a little bit. But if you want to zoom in at 0, they're almost the exact same equation. So, instead of calculating the exact sine curve for every single frame that you're animated, which would be really slow, it would be difficult for the computer, and it would take forever. I guess I already said that, but it could just simply use this polynomial graph, which is way easier and follows the exact same curve. It's way easier, faster to compute. And yeah, so that can be way easier for animating. If it's something, you can just use Taylor functions to, tripping up on my words. Basically, Taylor functions can help animators simplify their equations so they can animate things a lot easier, smoother, and faster. How do I turn this off? Oh. So we just talked about how Taylor functions can help the computers compute things more easily. And now I'm going to talk about parametric equations because they help animators create simpler equations. Instead of trying to match x and y in a complicated way, we can just use parametric equations to describe xy positions because we have a third variable. So this example is basically, say you're animating something that's traveling in a circle, and I chose a circle just because it's easy to conceptualize and think about. Instead of trying to think, I guess it would be okay if you used x and y for this because it's simple, but this is the starting one. We can think after 20 seconds, if we wanted to know after 20 seconds, where is the position of this thing going to be? We can use a parametric equation. So say that x of t equals 5 cosine of t. So this is how the x coordinate is related to time. Y of t equals 5 sine t. So normally, like in the example I showed, you would solve for t and just plug it back into each other's system of equations. But because we have cosine and sine, it's a little bit different. So we use this sine rule, trig rule. Sine squared of x plus cosine squared of x equals 1. So now we need to solve these for sine and cosine. So we would divide this one by 5, and divide this one by 5. So now we can think x over 5 equals cosine, and y over 5 equals cosine. I meant to say sine. This board is dirty. Now, we can just plug it back in here. X over 5 squared plus y over 5 squared equals 1. And now we have our equation that properly relates the y-coordinate and x-coordinate to time. And I have it graphed on Desmos, so let's go. Okay. Pretty sure it's recording. I don't have many free attempts on this platform, so as I was talking about, let's demonstrate something as it moves in a circle in relation to time. So here's the relation between the x-coordinate and time. Here's the relationship between the y-coordinate and time. If we put them together, if we solved for them like we did before, it'd be x squared divided by 5 plus y squared divided by 5 equals 1. So here's our graph, and I just used this little input method. Oops, I used this little way that Desmos likes to show it, to just show the exact same thing. So basically, where's the point? There we go. We can show how as we increase time, what the relation between the x and y coordinate is. So at 4.2 seconds, it will be, or let's do it somewhere we can actually see. At 4.07 seconds, it will be around -3, -4. And we can see it's going to be moving counterclockwise. So that just shows the relationship between xy coordinates and a third variable, time. And this is really helpful for animators because they don't always want to have to deal with just x and y. They just want to be able to say simply, succinctly, at 3.7 seconds, where am I going to be at? Where is my animation going to be at in its rotation? So there we go. And I have a little bit more complicated one to show you too. Okay, so we were just talking about how animators can use time to help understand different equations better, but I have a good one to show why you can't always just use x and y very simply. Say you're trying to animate something maybe like the solar system where it's sort of expanding. So you have something rotating and it's getting bigger and bigger and bigger. It's spiraling. And say this is your graph and you're trying to animate this. Say this is a star. That's kind of weird looking. Anyways, it's pretty complicated to say. If you want to know your x-coordinate here, it can be confusing because look, we have the same x-coordinate here, the same x-coordinate here. We're going to have the same x-coordinate all these different times. So how can t help? Well, we can just say, well, what is it at 50 seconds? Boom. What is it at 10 seconds? Boom. First is trying to say, when is it going to get here? Well, at x equals 2. Well, x equals -2. You say, oh, well, x equals 2 is also here, 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 here. So time can just help us locate specific spots. And I have some equations to show this. I didn't actually go through and solve all of them just because it was more simple just to put it in the way that Desmos can understand it, but I will write them out. So for the two equations, x is related to t by v equals 0.1 t times cosine t. This is the oscillating part, and this is the part that's going to help it grow a little bit over time. Y related to t is equal to, it's basically the same thing, but you substitute in sine because you're using sine values. This is going to make our equation that's going to look like this. Now, these are going to be complicated to compute. We already talked about these, so I didn't really think about this now, but I'm pretty sure that if you're animating this, this would be a really good problem because you'd have to work in Taylor functions into this because cosine and sine are already hard to compute. But let's go to Desmos to look at the graph. I'll just show you this. I was just kind of going through some really weird functions just to see how weird that parametric equations can be. It's kind of off topic, but you could have some extremely weird things to help you show the path of animated objects. But let's go back to this one. So we have our equation. This represents the x coordinates. This represents the y. You can see how it's growing. And if you put them together, which I just use this little Desmos input method instead of trying to actually calculate it, you get this spiral equation. Then I made this little guy so it can go along. See? I didn't go all the way to 50 because it gets a little wild. Once you get a little, it's just the larger you go, the more glitchy it is and kind of hard to say. It doesn't really matter. You can go up as high as you want. But I decided to go to 25 just because it was smoother. But you can see as t increases, it's going to be moving counterclockwise. And this can help animators because they can say, at 19.5 seconds, what's the coordinates? There. Really easy. Instead of having to worry about, again, the complicated ways in which y's and x's interact, we can just use this simple parametric equation that it really is just way easier for the animators to use an equation like this than to try to think about x and y. So this equation just helps them. I feel like I'm saying simply a lot, but it just helps them understand the movement of the things they're animated a lot easier.
Let's go over what I just said, just to clear it up. This little tune might help it stick, I hope I don't mess up. First we learned about parametrics, pretty handy you've got to say. They join two functions into one, they're much better that way. You want to know your x and y and how they relate to time, but you need it to be simple so you don't hurt your brain, then my friend you're doing just fine. First solve for t in terms of x and put that into y. After that you're pretty much done and your equation should apply. We're halfway through this melody now, I hope we'll clear things up. This little tune might help it stick, I hope I don't mess up. Next we learn about Taylor series, they'll clear things up all day. It's hard for computers to do some things, but with these they'll shout hooray. Euler's so tricky and so is pi, but don't forget about sine, because all these things are just so weird the computers will surely whine. So if you want to help them out, Taylor's formula's for you. Follow it exactly step by step and you will breeze right through. It makes a graph that's pretty close to the one you had originally. It's plenty good for what you need and it makes your animation run smoothly. So that's a recap of things I said, I hope this clears things up. This little tune might help it stick, but I hope I didn't mess it up.